As you can see, this is the PowerPoint for Anacortes High School Chemistry's Chapter 2. We're starting with matter and change. One of the things I want to draw your attention to is on each of the slides, I'm going to highlight, once I'm done with the slide, I will highlight information that I view as the key information for that slide. If you are taking notes, you would want to consider that information to be, at the very least, the information that you include. One of the habits you want to get away from with note taking is trying to write down every single word that's on every single slide. So we're starting today with properties of matter. And so we asked the question, what is matter? So why we ask this is that chemistry is the study of matter, energy, and its changes. So most of this year we're going to be looking at how matter changes, and then later on we'll look at what energy has to do with this. So the question, what is matter, is that matter is anything that takes up space, has a volume, and has mass. Now one of the things you want to be aware of right now is that volume and density are two different things. Volume is how much space something takes up, whereas density is a relationship between how much it weighs and the space it takes up. So just be very, very cautious about that. Now, you may notice the word there's mass in there, and so we need to define mass. Mass is the amount of matter that an object contains. In my opinion, this is the most least satisfying set of definitions in chemistry because it's a circular definition. We're using we need mass to define matter, then we're using matter to define mass. But we can work with it for now. And the issue is that there is a better definition of mass, which you'll learn when you take physics. So for now, let's just bear with this. So think about matter takes up space. You can put it on a scale, and it has mass. Now, one of the terms that we deal with then is substances. So what are substances? So some examples of substances are sucrose, otherwise known as table sugar, is a substance. Um, Anything that we can kind of give a chemical name to is a substance. And what all substances have in common is they are a kind of matter, and they will have a uniform and definite composition. So let's talk about what that means for a moment. So there's two pieces of information there, uniform and definite. Uniform means it's the same everywhere, or same throughout. Think about like a football team. They have a uniform. Everyone looks the same. Police officers have a uniform. They all look the same. Military professionals have a uniform. They look the same. So substances will look the same throughout. You look at it, you sample it, and it's the same throughout that sample. Definite means that it is stuck that way. It cannot be any different. So the example of this is like sucrose, table sugar, being a substance means if I have a sample of pure sucrose, that anywhere that I draw from in that sample is exactly the same. Whereas, it also has a definite composition, because if I get sucrose here in Anacortes, or if I get pure sucrose in New York or China, if it's pure sucrose, it will be the same everywhere. It cannot be any different. So we kind of have these three options here. So lemonade, air, and water are these substances. So we can apply our test. Does it have a uniform and definite composition? So let's think about this. Is lemonade a substance? So we ask ourselves, is lemonade the same everywhere? And hopefully you would recognize that the answer is no. Some lemonade is more tart than others. Some lemonade is sweeter than others. Some lemonade is extremely lemony. Some lemonade may only be lemonade, and that you have a jar of sugar water that you waved a lemon somewhere in its vicinity. So lemonade can be different, does not have a definite composition, and therefore not a substance. Air is a tricky one. One, people forget that air is in fact matter. Air has mass. We're just not used to it, or we don't see it because we're used to it. So again, let's think about this. Is air a substance? Is it the same everywhere? And does it always have to, is it the same throughout? Well, anyone who's traveled anywhere will recognize that air is not a substance. Uh, Air definitely fails the definite composition test. The air here in Anacortes is pretty pleasant. But if you go to some place like Colorado, because of a higher altitude, has a lower oxygen content, so it can be different. Therefore, it's not a substance. And water is a tricky one. Water depends on what you're thinking of. If I say tap water, the answer would be no. The tap water in one place is different from the tap water anywhere else. If anyone has lived in different areas, you know that different areas have different tap water. Again, it fails the definite composition test. Interesting little note is, I'm not sure you've heard of this, but in people say that New York pizza is the bee's knees of pizza. And I actually saw a program where you had a New York pizza chef making New York style pizza with water from 3 different areas. I think it was New York water, Chicago water, and Los Angeles water. And they had this board of people that were New Yorkers who'd been transplanted to other places. And they could actually tell which pizza was made with the New York water, because New York water has kind of a really apparently unique set of minerals dissolved in it, giving it a very special taste, giving the pizza something unique. So tap water can be different as you go from place to place. So tap water, not a substance. But if I said pure water is a little bit different. Pure water is a substance. Um, H2O, it has a chemical formula. But we very rarely deal with pure water, so that's why that one kind of throws us for a loop sometimes. And then here are my highlights. Notice I'm not not highlighting complete sentences. I'm just highlighting the minimum amount of information so that I have all the key pieces of information on that slide without writing everything. And here is just a very terrible joke. If you get it, congratulations. You've now had a preview of my sense of humor. If you don't get it, that's okay. Just let it go. Okay, now we're talking physical properties. So every matter, or all matter, has physical properties. So what are those? A physical property is something I can tell about a substance without changing what it is. And because all substances, well, all samples of a substance have identical physical properties. So we want to stress the word identical. This is because of that uniform and definite composition piece. That we often use physical properties to help us identify things. So if we have a white solid that we don't know what it is, and I know it's either salt or sugar. It's a big difference if you're cooking. How can I tell these apart? Well, one of the physical properties of these that I can tell is that salt will not melt on a tabletop stove. So I put some of the white powder in a pan. If it melts, it's not salt. But again, anything that I can tell about something without changing what it is, without creating a new substance, is a physical property. Here's some examples of physical properties: color, mass, odor, hardness, density, melting point, boiling point. The melting and boiling points trip people up sometimes because they think, if you take water, imagine like a liquid water, cup of water, and you freeze it, you now have ice. Ice and water are the same thing. You've just taken the water and changed its state of matter. It's still water. Likewise, if I take a cup of water and I boil it, it's still water. It's just water vapor. So going through changes in state do not change the substance that we're dealing with. A very common misconception. So we can often use those, and those are really, really critical physical properties, in fact. And you can think about this. You probably use physical properties to tell one person from another. If you see someone walking down the hallway, you look at their size, you look at their color, perhaps you look at what they're wearing. Hopefully you don't have to use their odor to really test this, and you probably should not use their melting and boiling point. But we use physical properties to identify people even. Nothing unusual about that. And like I've said, we use these physical properties to help identify different substances, one from the other. So speaking of states of matter, let's talk about them. So again, the same substance like water can exist in multiple forms. In fact, every substance can exist in multiple forms. So like water can be ice, can be water, can be steam. It's all the same thing. Hopefully, that is not a mind-blowing revelation to you. If so, you need to go back and talk to your middle school teacher and demand a refund because something has gone horribly awry. Now, these different forms of water are called physical states, and again, drawing attention to that word "physical," they are changing. They have only changed physically. They have not become something new. And again, these physical states are a physical property of matter, like melting, freezing, boiling, all that good stuff. So pretty straightforward on this slide. Okay, so now we're going to start talking about these different states of matter. Now, conventional wisdom tells us that there are three states of matter: solid, liquid, and gas. And I know that there are some of you out there right now who see this and they go, aha, I've got you, Mr. Anderson. There are not three main states of matter. There are four states of matter: solid, liquid, gas, and plasma. And you'd be right. We are just going to ignore plasma for now. Those of you who are particularly nerdy or smart, I'm not sure I'm going to draw a great distinction between the two with that, may recognize, aha, I've got you again, Mr. Anderson. There are five states of matter. You have forgotten the Bose-Einstein condensate. And I will reply, I have not forgotten it. I just would rather not deal with it because you do not have your doctorate in chemistry or physics. So we will ignore that. So starting with solids. So what's going on with solids? So first off, with each state of matter, there's kind of three things we want to look at. We want to focus on how its shape and volume compare to the container that it's in. And we can see here with solids, their shape does not depend on the shape of the container. If I take a stapler outside, it does not change shape. If I bring my stapler into a circular room, it does not become a circle. So its shape is independent of its container. Volume, they also do not take on the volume of its container. If I bring my stapler outside, it does not grow huge. If I bring my stapler into a small room, it does not shrink. And the last thing you want to focus on is what the particles are doing. So what's going on with the particles in this solid that's causing it to keep its shape, keep its volume? And what's happening there is that in a solid, the particles are packed together extremely closely. Because they're so closely packed together, most solids are incompressible. You can't squeeze it down anymore. You might be able to get it to expand a little bit when it's heated. So one analogy you can use with this is think about your high school. Imagine taking all the students in your high school and packing them into one hallway. Everyone's packed together as closely as possible. No one has room to move. No one person can move independently from the rest unless you're at the edges, and we'll just ignore that for now. But that's kind of what's going on with this. So now on to liquids. So liquids the particles are still touching like they do in a solid, but they're packed together much less tightly. So if a solid is all the students crammed in one hallway, think of maybe like the liquids, all the students packed together in one floor of a building. Chances are, unless you're in a really small school, that it's still going to be really crowded, but you now have room to move. And one person can move past another. You might be bumping shoulders, um, but it's possible, or like moving around at a big concert, something like that. Now, because um, the particles are still touching, they're pretty much still incompressible. There's not enough room to really push them down, which anyone who has done a belly flop in a swimming pool is aware that water does not compress. It actually takes time to move around you. Uh, now, but because there's now room for them to move, we can say that liquids flow. And that means it takes on the shape of the container in which it's placed. Um, which should make sense. That think about as you drink water from, let's say, a water bottle. The water starts off in the shape of the container that it's in. Then it passes through the nozzle, and it takes on the shape of the nozzle. Then it's in your mouth, and it takes on the shape of your mouth. Then it's running down your throat. It's taking on the shape of your throat. It's in your stomach. It's taking on the shape of your stomach. If it couldn't do that, it would be nearly impossible to drink water. Try to imagine drinking an ice cube. You'll die, and that would usually be quite unpleasant. But again, back to this incompressible piece, the particles, because they're still in contact, the volume remains the same. So if I have a gallon of water and I pour it out on the floor, I'm still going to have a gallon of water. It's just that the shape will be different. Instead of being shaped in a gallon-shaped container, it will be trying to take on the shape of the floor, but the volume remains the same. And we can see here with this drawing on the right, just the little infographics that I've stolen from the internet. And my notes. And now we move on to gases. So gases will flow to take the shape of the container that holds them, so they're like liquids in that sense. But we want to imagine what's going on with the particles here. So the particles in a gas would be like all the students in the school going home at the end of the day. They just spread out completely. So they're going to take on the shape of their container. They're going to take on the volume of their container. And they're going to space themselves out as far apart as possible. And because they space themselves out, there's lots of room between the particles, so they're easily compressible. So if you've ever heard of compressed gas, this is how we do it. Pretty straightforward. Now, just for a point of vocabulary pickiness, the word gas is not the same as the word vapor. We use the word gas to talk about something that exists as a gas in the gaseous state at room temperature. We use the word vapor to describe something that might happen to be in the gaseous state, but is generally a solid or liquid at room temperature. So for example, we can talk about carbon dioxide gas, oxygen gas, neon gas. These are all things that are in the gaseous state at room temperature. But water is normally a liquid at room temperature. So we would say if we've boiled water, we have water vapor. So that's the difference there. So a little bit of vocabulary pickiness, but you can expect to see that later on. Okay, I mentioned that chemistry is the study of matter and its changes. So there are two sorts of changes we're going to deal with. The first are physical changes. And again, we know that matter can be changed in lots of ways without changing what something is. So cutting, grinding, bending, melting, freezing, boiling. That is not an exhaustive list. But those are all things I can do to matter without changing it. If I take a piece of paper and cut it in half, it doesn't magically become some new substance. It doesn't chemically become something else. It's still paper. There's just two pieces of it. So it stayed the same stuff. We call that sort of change a physical change. Physical changes are changes that do not change what we're dealing with. Now, this doesn't always work, but you can kind of use that. Most physical changes, are reversible. It might be difficult to do, but you can do it. So for instance, if I have ice cubes and they melt, I do not just cry and beat my chest and go, oh, my ice has forsaken me, I shall never see it again. No, we just refreeze it. We can turn it back into a solid. We can undo that phase change. Um, Other things are a little harder. So if you cut a piece of paper in half, how can we put it back together? There is actually a way. If you actually shred the paper up into little bits and pieces, add water, push it all together, smash it together, it can actually fuse back together into paper. As weird as that is, that's kind of how paper is made, especially recycled paper in a real simplistic format. But physical changes, we do not change what we're dealing with. We just kind of change how it looks. Okay, now we're moving on to section 2.2. So we're looking at mixtures. So what this is really focusing on is types of matter now. And section 3 is going to look at different types of matter. So mixtures are a type of matter. So what does it mean to create a mixture? What is a mixture? So some examples: salad is a mixture, soil is a mixture, lemonade is a mixture, air is a mixture. Now, if you were paying attention in section 1, you may remember that we had a conversation about substances, and we saw lemonade and air being discussed there, and we were determined that those were not substances. And that's really what a mixture is. Mixture is matter that's not a substance. And it's because it's just a physical blend of substances. It's made of substances that happen to be in the same area at the same time. But they can be physically separated from one another. So I can filter out things. So for example, if I have soil, I can put a fine grate and shake the soil through it, and the fine soil will fall through, leaving the rocks behind. Evaporate. If I have salt water, by the way, this is actually how they kind of make sea salt in some places, is they take these basically giant cookie pans, lower them into the ocean, scoop it back up so it's filled with salt water, filled with ocean water, and they let the water evaporate, leaving the salt, and they just kind of deal with that. You can sort stuff out. So let's say you have a salad. Now, there's certain toppings that belong on a salad, certain toppings that don't. So for instance, salad, lettuce, tomatoes, mushrooms, black olives, all good stuff. Croutons, good times. But let's say some foul demonic being puts cheese on a salad. That is the fastest way to ruin a salad that I've ever seen, by putting cheese on it of any type. It's never acceptable. At that point, you can just pick the cheese off, as any right-thinking person does. Chromatography is another example of this. Chromatography is a technique where you can actually separate pigments based on kind of how attracted they are to the water in the paper. And it can actually turn inks that look like one thing, and you can actually see that they're made of all these other different colors. So again, we have this physical blend, not a substance, physically separated. Okay, so granite, salad, air, Kool-Aid, those are all mixtures, but let's think about how they look. In general, we should see a difference. So I'm going to kind of give a hint. So granite and salad tend to be one type of mixture. Air and Kool-Aid are another type of mixture. So what's going on with those? What's the general thing that we look like, or that we see? We'll hopefully recognize that in something like granite or salad, it looks like it's made of different things. If I see a salad, I can see the lettuce, the tomato, the mushrooms, the olives, the croutons. I can see all those pieces. If I look at a piece of granite, I can see all the minerals making it up. Air looks like it's one thing. Kool-Aid looks like it's one thing. So that tells us there's actually two types of mixtures. The first type we're going to look at is called a heterogeneous mixture. This is where, if you remember some of your root words, this may help. So when you see the root word hetero, think about what that means. It means different, so it looks like it's made of different things. The heterogeneous mixtures, being mixtures, fail the uniform and composition test. Remember, substances are uniform and definite compositions, which means it's the same throughout. That's what uniform means. And it's the same everywhere. That's what definite means. Mixtures as a whole are not substances. But heterogeneous mixtures will always fail the uniformity test. It is not uniform in composition. It looks like it's different. If I sample one portion, it's going to be different from a sample of another. So imagine you're eating a salad and you're just stabbing blindly down at the plate with a fork. You stab down once, you get a piece of lettuce. You stab down and again, you get a tomato. You stab down again, you get your sibling's hand who is trying to steal a crouton. They get what they deserve. Um, that's what makes it a heterogeneous mixture. And I already answered that question. Now, the next type of mixture is the opposite of a heterogeneous mixture. So if a heterogeneous mixture looks like it's made of different things, the other type is called a homogeneous mixture. It looks like it's made of one thing. It has a uniform composition, but it is not a substance. It still fails the definite composition test. And again, we can use our knowledge of root words here. I see homogeneous or homogeneous. Again, root word homo means same. Funny story about this is years ago, I was teaching a biology class. And we were talking about, we were doing with Punnett squares and genes, and I was talking homozygous versus heterozygous, and asked the same question, what does the root word homo mean? And this girl who never really answers questions struggled in class. Her hand shoots up, and I call on her. And very proudly, she says, gay. And I have to say, close. You're so close. Um, so yeah, little tangent there. But if I have a homogeneous mixture, it's going to be the same throughout. Now, its compositions can still vary. Lemonade should be a homogeneous mixture. Should be. If it's well mixed, it should be. But it's still a mixture because different lemonades can be different. So its composition can still vary. Okay, a term that we use when we're talking mixtures is phase. Phase is any part of a system with uniform composition and properties. That's the kind of official textbook definition. I like to think of phase as how many different things can we see. Every different thing that we can identify in a mixture is a different phase. Homogeneous mixtures, because they look the same throughout, have just one phase. All homogeneous mixtures all have one phase. Heterogeneous mixtures will always have two or more phases. They look like they're made of different things. So just kind of be aware of that. Okay, now we're on to section 2.3, elements and compounds. So previously we spent a time talking about two categories of mixtures. And again, we saw earlier that there's now two types of matter. You have substances and you have mixtures. So today we're going to talk substances. And just like mixtures, there's two types of substances. And the very astute amongst you right now might be looking at this slide and can figure out what those two types of substances can be, elements and compounds. So let's start with elements. The official definition of an element is the simplest form of matter that can exist in normal laboratory conditions. And because it's the simplest form, it cannot be broken into anything simpler by chemical reaction. So there is no chemical or physical process you can go through that can make an element any simpler. Now, just for the sake of completeness, nuclear reactions can. We call that nuclear fission, but we're not going to get into that this year. Easiest way to tell an element is look at the periodic table of the elements. If it's on the periodic table of the elements, it's an element. Common examples of elements that we deal with semi-regularly, or you might have some familiarity with, iron, sulfur, carbon, hydrogen, oxygen. All of these are elements. And we can see down here at the bottom that all elements have this kind of chemical symbol thing going on, so we can represent elements symbolically. Okay, second sort of substance we're going to talk about are compounds. Compounds are still substances, but they can be broken into simpler things through a chemical reaction. Um, and compounds are made when two or more elements combine chemically. Now, one of the things I want to stress, and there's a word missing from this statement that I want to throw in, two or more different elements combine chemically. To be a compound, it has to be made up of two or more different elements. Now here I say chemically as opposed to physically, because if I combine things physically, what do I get? I get a mixture. Common examples of compounds that we deal with regularly: water. Um, hopefully you're familiar with water, probably unless you're in Arizona or California. And octane. And octane is one of the major components found in fuel, gasoline. Now, if you have your textbook around you and you use it because you are a unique student, on page 38, there is a flow chart that summarizes everything I've discussed so far in this chapter. So if you are the flow chart loving sort of student, check out page 38. If you are the sort of student who is brought into a frothing rage at the sight of flow charts, probably best to just let that flow chart go. Now, this is one of my favorite ideas with compounds, is that the properties of compounds are wildly different from the properties of their individual elements. So, for instance, sugar. Standard sugar, sucrose, is a compound made of carbon, hydrogen, and oxygen. And we know what sugar looks like and the physical properties of sugar. We know it's sweet. We know it's usually a white crystal, solid at room temperature. So let's talk about the elements that go into it. So carbon, the standard elemental form of carbon is graphite. So think about if you're writing with a pencil, that's carbon with a little bit of wax to hold it together. Charcoal is effectively carbon. Hydrogen is a clear explosive gas, most abundant element in the universe. And then oxygen is a clear gas that helps things burn. And as an interesting note, in its liquid form, is slightly blue and magnetic. Really weird. So we take black charcoal, explosive clear gas that helps things explode, and we get sugar. Now, the one that's even better is table salt. We're all familiar with table salt. I love salt on my food. Table salt is made of two elements, sodium and chlorine. Sodium is a silvery metal, very soft. You can cut it with a butter knife, that has the very interesting property that it explodes when you put it in water. Good times. And then you have chlorine, which is a gas at room temperature. It's green and is horribly, horribly deadly. If you inhale chlorine gas, it actually reacts with the water in your lungs to form hydrochloric acid, so your lungs start to dehydrate, and because it's reacting with the water, and then the hydrochloric acid starts destroying the lining of your lungs, so you can't process oxygen. So if you inhaled a large amount of chlorine gas, you're going to die pretty terribly. But we can actually take silvery gray explosive metal, combine it with green murderous gas, and we get table salt that we put on popcorn, food, everything else. So again, properties of the compound, very, very, very different than the properties of their elements. Okay, so again, all matter in the universe is made up of elements. Elements can get together, make compounds. Compounds and elements can mix physically to make mixtures, but all starts with elements. And every element is represented by some chemical symbol. And a chemical symbol is a one or two letter combination where the first letter is always capitalized. Always, always, always. Now, if you have some periodic tables, you may notice that there are some elements that have three-letter chemical symbols. Those are newer elements that have not been given official names. Now, depending on the age of your periodic table, some of those may have names at this point, but your periodic table was just written too long ago. Generally, the chemical symbol will consist of the first one or two letters of the name of the element. So for example, carbon is C, lithium is Li, neon is Ne. So most pretty easy to deal with. Um, so that works out really well. But this isn't always the case. Some elements are derived from older Latin names. I think there's a few Greek ones, and there's even one German one. So example, sodium has the chemical symbol of Na because its Latin name was natrium. Interesting note, I had a student a few years ago from Azerbaijan, and they still call sodium natrium. So I thought that was really interesting. Copper is Cu for cuprum. Gold is AU, was called Aurum, and now the one that always makes students titter whenever I say it, so feel free to titter at the screen if that is your desire. Lead is PB because its name was plumbum. Yes, plumbum. Interesting note about this, the word plumbum is actually the same root that we use where we get the word plumbing. That's because in Rome, they would actually use lead for their plumbing. So there is a linkage between there. I did mention that one element came from a German word. That's tungsten. Tungsten has a symbol of a W, and you might wonder about that. Tungsten comes from the German name for this called Wolfram. And apparently it was named this. I can't remember which World War because I'm not a history teacher. But the Germans made these giant cannons that were made to shoot miles away, I believe. And they were finding that the heat generated was causing the steel to melt unless they kind of alloyed the steel with tungsten, making tungsten making tungsten steel. And it was much harder. So they named this new element Wolfram, for the German word for strength. And why do we use these chemical symbols? They really give us a shorthand way to write chemical formulas. So for example, water. Most of you probably learned back in elementary school, probably even before you knew what this really meant, that water has the formula of H2O. That's its chemical formula. Um, why do we do that? Well, because as chemists, we are efficient, not lazy. We are efficient. And instead of saying that we have a compound that's made from 2 hydrogens and 1 oxygen, because that's a lot of letters to write down, we can just write H2O and we're good to go. So that gives us a shorthand way to deal with this. And that's what this says too. So here we see sucrose. Sucrose has the chemical formula C12H22O11. So C is for carbon. So how many carbons would we see there? We look at the subscript. I'd see 12 hydrogens. We'd see 22. Oxygen, we'd see 11. And every time we see sucrose, again, sucrose being a substance, it will always be 12 carbons, 22 hydrogens, 11 oxygens. That's that definite composition piece, that if that formula changes at all, it's different. And that is what this says. Within a compound, the elements that make it up are always in that proportion. Water is always H2O, always 2 hydrogens to 1 oxygen. Changing the amount of chemicals changes the compound because it's a substance. We change what it's made of, we change the ratio, we change the compound. So for instance, H2O is water, essential for life as we know it. H2O2 is hydrogen peroxide, which will murder you. And you might think that I'm exaggerating at this point because you think, oh, hydrogen peroxide, that's that brown bottle. My parents put it on cuts. I'm okay. The hydrogen peroxide that you buy at the grocery store in the little brown bottles, that's only 3% hydrogen peroxide. 97% of what's in that bottle is water. And even then, it can do a number on tissue. When you go up to higher concentrations of hydrogen peroxide, it gets really, really scary, really, really fast. But again, change the formula, change the compound. And our final section of this chapter is section 2.4 on chemical reactions. So let's kind of take a step back. We talked physical changes a couple sections ago. And a physical change is something I can do to a substance without turning it into a new substance. Chemical reactions or chemical change are the opposite of that. So a chemical reaction or a chemical change, we are changing the substance into a new substance. We are creating new matter. We are creating new stuff. Whatever substances we start with, we call the reactants. I always remember this because it's the reactants that are reacting. Whatever substances we end with are called the products. And I just remember that is what the products are, what we are producing. That is the product of the reaction. And in a chemical equation, you will see this right-facing yield arrow. It's called the yield arrow. You can view it as are changed into. So what we're going to see is it's going to be the reactants on the left, yield arrow, products on the right. So the reactants are turned into the product. So we're going to go through a few examples of a chemical reaction and how we can write this down. So this example, iron and sulfur chemically react to form iron sulfide. That is a description of a chemical reaction. We could view it as this. And already, this is much more efficient because, well, there's fewer letters that you have to write. Iron, sulfur, iron sulfide. Now, see that plus there? That plus in a chemical equation does the same role as a space bar on a keyboard or a space in a sentence. It's telling us that there is a separation between those. So there's iron and sulfur. Those are two separate substances separated by that plus sign. Whereas on the product side, the right side, we see iron sulfide. There is no plus sign, so that's all one substance. And we can see reactants and products. Now, what are some indications that a chemical reaction has taken place? And I want to point out before I go into this that all of these, you do have to apply some degree of common sense. So if I mix two room temperature things together and it becomes warmer or colder, that's an indication of a chemical reaction. But if I have a pot of water on the stove and I'm heating it up and the water becomes hot, it should not surprise us that the water is hot because we've been heating it up. So that would not be a chemical reaction. But mixing two chemicals together at room temperature and suddenly they start to get very hot, that's a sign of a chemical reaction. Color change, great way to tell if there's a chemical reaction. Because in a chemical reaction, we're creating new substances. New substances have new physical properties, so we can often see new colors being formed. Production of a gas or a solid. And again, I'm mixing things at room temperature. I mix two liquids at room temperature, and suddenly we see bubbles forming. It's not because it's boiling. Those bubbles forming are because we're producing a gas. Or I mix two chemicals together at room temperature and we suddenly get a solid where there was no solid before. We're not forming a solid because we're freezing it. We're forming a solid because the new substance we've created happens to be a solid at room temperature. And bear with me on this one. A general indication doesn't always work. It kind of goes along with the physical changes earlier. Most physical changes can be reversed. Most chemical changes cannot. Think about cooking, for instance. Most cooking involves chemical changes. So let's say I'm cooking a steak. As I cook a steak, so I put a steak in a hot pan and I'm cooking it. So what are some indicators that there's a chemical reaction going on? Well, one, I notice the steak changing color. I'm not painting it brown as it cooks. It's turning brown because I'm creating new substances. Also, it can't be reversed. If I overcook my steak, I can't put it in the freezer and uncook it. Once it's overcooked, it's overcooked. But again, you do have to apply some modicum of common sense. Now, chemical properties. Just like there are physical properties, there are chemical properties as well. what a chemical property describes is, can something undergo specific chemical reactions to form new substances? Chemical properties are the trickiest of them because a chemical property will tell you if something will or will not undergo certain chemical reactions. And we can only tell or see these chemical properties when we try to do it. So, for instance, here's kind of a list of words that often are associated with chemical changes. Rot, rust, decompose, ferment, corrode, grow, decay, burn, react. So if something can rot, that's a chemical property. If something will not rot, that is also a chemical property. Burn. Carbon being able to burn, being able to combust, is a chemical property of carbon. Steel not burning is a chemical property of steel, although I should say iron instead of steel because we're talking substances. So that's kind of the idea here. It's whether it happens or not happens are all chemical properties. Now, along with chemical reactions, there's a very, very, very important rule that undercuts all sciences, and this is conservation of mass. And what the law of conservation of mass tells us is that in any physical or chemical reaction, mass is not created or destroyed, it is conserved. Interesting bit of history. You don't need to know this for any opportunity, but just good to know. I don't think it's interesting. This was actually found by a French couple named the Lavoisiers. And the husband, Antoine Lavoisier, was a tax collector in Paris before and shortly into the French Revolution. And he spent a lot of money that was collected from taxes to fund these experiments to show that during any chemical or physical reaction that he did, that the amount of matter stayed the same. It could change forms, it could change how it appears, but the amount of matter stays the same. Unfortunately, for those of you who know your history potentially better than I do, you may know that tax collectors during the French Revolution were quickly executed. So Antoine Lavoisier was killed during the French Revolution. He was not liked very much. But that's neither here nor there. One way you can look at this, and the good way to think about this, is because mass is conserved, the mass of the products will always equal the mass of the reactants. If I have 10 grams of reactants, I'm going to have 10 grams of products every single time during any physical or chemical reaction. And that is it for this chapter. Thanks for paying attention.